It's time to get your arrows popping. Ladies and gentlemen, it's me, Mr. Whitt with Fort Bend Tutoring, and today's tutorial is going to be about integrating using the change of variables technique. That's right. It is also called u-Substitution if you want to know, and we have some examples in store for you today. But first, please go ahead and subscribe. Click that subscribe button and also click on the notification bell icon. We would greatly appreciate you joining us for future videos when we upload them to our YouTube channel, Fort Bend Tutoring, FBT. So let's go ahead and dig into our video today. Notice that I have a few things outlined for us to take a look at during this video. First of all, I wanted you to be able to associate the phrase change of variables with u-Substitution. That's the first thing. Number two, I have 10 examples to present to you today, and it's going to involve some functions with square roots, rational functions, definite integrals, and trigonometric functions, all wrapped into this one FBT online tutorial video. You got it, guys. So let's go ahead and move on to our next page, where I have a list of integration formulas that we'll be using during this video. What I wanted to showcase here is that I have the power rule for integration as number one. Number two, we're looking at the reciprocal integration rule here. Number three, we're dealing with integrating a function with a natural number base, or Euler's number, and we have some trigonometric functions. And just keep in mind, anytime you see u written in this video, guys, it is representing a function of x. Amen, amen. So without further ado, let's go ahead and look at problem number one, where we have number one with the integral of 2x times the quantity of x squared plus 1 squared, and it has been derived with respect to x. That's that dx part of our expression here, showing that the original function was derived with respect to x. If you know anything about integration, guys, we're trying to find the original function where this expression came from, okay? So that's one way of looking at it. Also, you should know that finding the integral of an expression tells you the area of the graph of that expression with respect to the x-axis in most scenarios. So the first thing I want to show is that notice how we have practically two functions multiplying on one another, right? We have the 2x, it's multiplying on our x squared plus 1 squared, and we're asked to integrate this. When using u-Substitution, aka change of variables, the first thing I want to identify is a portion of the expression that, when derived, can look like the other part of the expression. So what do I mean by that? First of all, if we let u be equal to x squared plus 1, notice that when I take the derivative of this, and I'll showcase this by saying the derivative of u is equal to 2x with respect to x. Notice that I derived both sides of that equation that I made when I said that u equals to x squared plus 1. And on the left side, we're saying the derivative of the function u is going to be equal to 2x, stating that we derived at x squared plus 1 with respect to x. That x was our independent variable in that expression. So what we want to highlight now is that we can find 2x in our original integral. We can also find dx in our original integral. And with this, we can now rewrite the original problem. We can now rewrite it as the integral of u squared du. Notice that this u is being represented by the x squared plus 1, right? And since that original x squared plus 1 is squared, we have our u squared. In addition to that, we are saying that our du is going to be representing the dx as well as the 2x there. So that's why this process is also known as u-Substitution, because we're using the variable u and its derivative to replace much of the original content from the original integral. So now that we have arranged it in this format, we can now integrate it using one of our integral formulas that I showed you earlier. In fact, it was the first one, the power rule of integration. I'm going to use the integral extension here to show where this is the point where I'm actually integrating the expression. So with that power rule method of integrating, and you can check out our video on integrating using the power rule, you'll end up with u to the third power over 3 plus your arbitrary constant c. Remember that we're trying to go back to the original function that the 2x times x squared plus 1 squared was derived from. And when you're taking the derivative of any constant, it becomes 0. And so that's why we'll need an arbitrary constant of c here to show that the original constant from the original formula could have been any number. We don't know what it is. So that's why it's going to become our arbitrary constant. Depending on the problem, you may have enough information to find out what that original constant is. But if you don't, you'll just leave it as the arbitrary constant c. So the next thing I'm going to do is I'm going to rewrite our previous step as 1/3 u to the third power plus c. So now I'll back substitute that x squared plus 1 back in for u, and we'll be able to rewrite this expression as 1/3 times the quantity of x squared plus 1 cubed plus your arbitrary constant c, and this is your answer. Red boxing it. Just like that, people. You have 1/3 times the quantity of x squared plus 1 cubed plus the arbitrary constant, and this is the answer to problem number 1. Let's keep it moving, people. On to problem number 2. Here we have the integral of 3 minus x to the 4th power cubed times x cubed dx. So we know that this original function was derived with respect to x because of the dx aspect of the expression here. And we want to first of all try to identify some portion of the expression that when derived will have a result that will look similar to the other parts of our original integral. So what I'm going to highlight as our u for this problem is 3 minus x to the 4th power. So then we derive this, and we'll end up with du being equal to negative 4x cubed with respect to x. All right. So it's important to make sure that you're including the dx there when you take the derivative of u. The next thing you want to do is you want to analyze your result of the derivative of u. Well, it's close, but it's not exactly what we had in the original integral, now is it? We have negative 4x cubed dx. However, in the original integral, we have x cubed dx. So that's when you're able to use your creativity in this process. And notice that if I divide both sides of the equation by negative 4, that when I simplify this, I can now rewrite it as negative 1/4 du will equal to exactly what we need, which is the x cubed dx, right? So now we have all of the pieces of the puzzle to rewrite the original integral. And how do I do that? I'm going to do it just like this. I'm going to say that I have the integral of negative 1/4 u to the 3rd power du. And even better, guys, going forward, I'm going to actually take that negative 1/4, that coefficient, I'm going to pull it in front of the integral symbol, and I'll have negative 1/4 times the integral of u to the 3rd power du. The reason why pulling that coefficient of negative 1/4 is so important is because format is everything when you're integrating. Notice that at the beginning of the video, I gave you guys that table of integration formulas. You want to be able to match your format to one of those or one of many different integration formulas so that you can make the process of integrating that much easier for you. So now that's when I'm going to go ahead and bring down that negative 1/4. I'm going to use my integral extension to show that this is the part that I'm actually integrating the problem at this point. And documentation is everything. It's not only for your teacher, it's not only for your classmates, but it's for you to be able to go back in a review and see exactly when you did what step when. So take my word for that on that, okay? So what I'm going to do is I'm going to use the power rule again, and I'm going to show that I'll have u to the 4th power divided by 4 plus c here. And with this, I'll be able to simplify this as negative 1/16 u to the 4th power plus c. And now back substituting our quantity of 3 minus x to the 4th power back in for u, I now have a solution that reads negative 1/16 times the quantity of 3 minus x to the 4th power raised to the 4th power plus c, and this is my answer. Red box it. Just like that, people. All right, let's go ahead and move on with our video here. As I remind you and ask of you to please donate using the donation link in the description box and on our About page on our YouTube channel. It helps us bring out more fresh material for you guys, giving you as much free content as possible on our YouTube channel. So go ahead and check us out. And if you're able, please donate. It all makes a difference. Thanks in advance, people. Here we have number 3, where we have a rational expression. You have the integral of dx divided by 3x plus 5. Well, there's actually a couple of other ways to rewrite this problem. You could say that this is equivalent to the integral of 1 over 3x plus 5 dx. That's another way of writing this. You can also say that it is the integral of the quantity 3x plus 5 raised to the negative first power dx. So in any of the forms that you see before you, you can go ahead and start using your change of variable process in order to integrate this problem. What I'm going to do first is I'm going to show and I'm going to label u as the quantity 3x plus 5. In doing so, I'm going to continue with finding the derivative of u, and then that derivative being 3 dx. Notice that in our original integral, we don't have the number 3 isolated anywhere in the original integral. All right, so that's something to keep in mind. But what can you do about that? Well, as I showed you in the previous problem, you could just divide both sides by 3, right? And by dividing by 3, we now can show that 1/3 du is going to be equal to dx. Now, see, that's something that you can use, because with this form here, we can now show that we can rewrite the original problem as 1/3 times the integral of u to the negative first power du. So now that we have it in this form, let's go ahead and use that reciprocal formula that I gave you earlier, and we'll have 1/3 times the natural log of the absolute value of u plus your arbitrary constant c. And with that, that simplifies further to 1/3 times the natural log of the absolute value of u plus c. And what was that absolute value? What is the value of u? Remember, our value of u is going to be that 3x plus 5. So you'll have 1/3 times the natural log of the absolute value of 3x plus 5 plus c. And because you don't know what the value of x is, we want to keep our absolute values here because we can't guarantee that that value is going to be greater than 0. Remember that your domain for the natural log of x is that x must be greater than 0. All right, so that's why we have to maintain our absolute value around the quantity of 3x plus 5. And this is your answer. Yeah, so let's go ahead and red box it. Just like that, guys. And that's number 3. Done and done. On to our next problem, people. We have problem number 4, and we have the integral of sine x divided by cosine cubed x dx. All right, so I see multiple trigonometric functions in this problem for number 4, which means that we're more than likely going to be relying on the trigonometric function integration formulas that we were given at the beginning of our video. If you're curious as to where to find your integration tables, more than likely your first resource is going to be your textbook, okay? Other than that, you have the entire internet full of integration tables. Okay, so you can go ahead and grab them there, and if you can't find them there, you can always stop by our online store where we sell formula sheets that you can use. All right, so keep that in mind. When I look at this, guys, you want to first of all determine what is going to be the best substitution that you can do that'll help you throughout this problem. And when I'm looking at this problem, guys, I'm thinking that the best quantity to call my variable u is going to be cosine of x. Yeah. That's what I'm thinking is going to work out for me. Taking the derivative of u, you'll end up with du of negative sine x dx. Notice that this is close to what we have in our original integral, but it's not exactly the same. But remember, using your algebraic foundation, you can manipulate the equation to get exactly what you need. And so that means that in this case, you can either multiply both sides by -1, or you can do what I prefer, and that is to divide both sides by -1. So that's exactly what I'll be doing right now. I'll end up with negative du equals to sine x dx, just like that. Yeah. And with this, I can now rewrite the original integral as the following. I'll have a negative integral of du over u cubed. Yeah. Or you could also say it's a negative integral of u to the negative third power du. If you write it as the latter, you can now see how I can use the power rule to integrate this problem now, right? So let's do just that. You'll end up with a negative, then I'll use my integral extension here to show that I'll have u to the negative 2 over negative 2 plus c. Simplifying, you'll have a positive 1/2 u to the negative 2 power plus c. Continuing to rewrite, you'll have 1 over 2u squared plus c, which gives us a result of 1 over 2 cosine squared x plus c. Red, box it, people. Just like that, that is your answer for problem number 4. How about that? All right, on to problem number 5. So in problem number 5, we have the integral of e to the 4 times the square root of x divided by the square root of x dx. This one looks a little wonky, does it not? Yeah, doesn't it look a little crazy? Let's go ahead and realize that 1, we have in the numerator Euler's number, the constant e, the natural number. If you think back to the beginning of the video, I gave you an integration formula just for a problem like this, okay? Almost like I knew it was coming, right? You know, it's crazy. So let's go ahead and note that our variable u is going to be 4 times the square root of x. Let's go ahead and say that. Even better, let's rewrite that and say that it's going to be 4x to the 1/2 power. How about that? Yeah? That's interesting, huh? Then, taking the derivative of this, you'll have du equals to 2x to the negative 1/2 dx. So after we took the derivative of both sides of the equation, what you'll want to do now is try to rewrite this into a format that's going to be useful for us. In other words, that we're trying to match a part of the original integral with our derivative of u. So let's begin by dividing both sides by 2. Let's do that. That should help, right? You'll end up with 1/2 du equals to x to the negative 1/2 dx. Okay. And what's even better about this is that if you were to shift that base of x to the denominator, that now becomes 1 over x to the 1/2 dx, right? And you can also say that this is 1 over the square root of x dx. Now that looks really similar, if not exact, to what we have in the original integral. So how about we show a little rewrite of the original integral? I'll show that I have the integral of e to the 4 times the square root of x times 1 over the square root of x dx, right? Therefore, I'm showcasing that e to the 4 times the square root of x is being multiplied by 1 over the square root of x to help us match that 1/2 du to the original integral. So I'm doing a little rewrite to make things clearer for myself. So I'm going to underline our 1/2 du, which is that 1 over the square root of x dx, to show that it's right here in the original integral. So now that we have everything matched up, let's go ahead and do some u-substitution, shall we? As well as considering that new 1/2 coefficient, you'll have 1/2 times the integral of e to the u du. And now, integrating, I'll have 1/2 using the integral extension to show that this is the point where I start integrating. I'll have e to the u plus c. Simplifying, you'll have 1/2 e to the u plus c, and then doing your back substitution, you'll end up with 1/2 e to the 4 times the square root of x plus c, and this is your answer. Red, box it, people. Just like that, with a Euler's number example. How about that? Not bad, huh? Okay, I got more to show you. Let's move on. Here we have problem number 6 with the integral of x divided by x minus 21 dx. And with this, remember the ideal is to identify one part of the integral that when you take the derivative of it, it'll look similar or identical to another part of the expression within the integral, right? Well, that's really not the case here. If I take the numerator and say that x is u, the derivative of x is 1. Well, that doesn't look like the denominator. And if we look at the denominator of x minus 21, the derivative of that would be 1, which doesn't look like the numerator, right? So we're in a little pickle. Okay, so this problem and the ones that follow may be the most important problems to you in this entire video, because this is the catch-all for when things don't work out perfectly. Okay, so let me show you this. We're going to first of all start with u being the denominator, the x minus 21. Now, why did I choose the denominator versus the numerator? Well, for starters, generally when you're doing your substitution and your change of variables, usually you want to substitute out the more complicated part of the expression. In this example here, the denominator has multiple parts when compared to the numerator, which just has x, right? So I'm going to choose the more complicated of the two in general. All right, not all the time, but you'll get a feel for it the more problems you do. So I'm going to have u being equal to x minus 21. Well, if I take the derivative of both sides, I'll have du equals to 1 dx. All right, so you could have written the 1 there, but it would have been redundant. You're going to also take this new equation, this u equals to x minus 21, and you're going to go ahead and solve for x, okay? And in doing so, you'll need to add 21 to both sides, right? Okay, you know how to solve for x, don't you? You'll end up with x being equal to u plus 21. Well, see, we want to hold on to that piece of information there, all right? It's going to come in handy. So what we'll do now is the following. We're going to now substitute in the values that we just found. What do I mean by that? Looking back at our original integral, you'll have the integral of x, which we know is u plus 21, divided by x minus 21, which we know is u, du. So recapping our substitution, guys, the u plus 21, we replaced the x in the numerator with that, okay? Looking at our denominator of u, we replaced the x minus 21 with that. And looking at our dx, we replaced the dx with du. So those were the three parts of the original integral that we substituted with u, with our new variable that we have. The next thing I want to do with this problem is I want to expand our rational expression that we have here, our fraction, right? I'm going to be able to expand this into the integral of u divided by u plus 21 divided by u du. And then simplifying, this becomes the integral of 1 plus 21 times 1 over u du. So once expanded and simplified, I'm going to use our sum or difference properties of integration to rewrite it as the integral of du plus 21 times the integral of 1 over u du. Prepping our problem for the power rule, you can show that this is the integral of u to the 0 power du plus 21 times the integral of 1 over u du, like so, and then integrate this to become u to the first power over 1 plus c1, our first arbitrary constant, plus 21 times, integrating this will be the natural log of the absolute value of u, plus our second arbitrary constant. And let's make a note that our first arbitrary constant plus our second arbitrary constant is just going to be an arbitrary constant called c as the total of all of the individual arbitrary constants that we obtained when we integrated those separate parts of our problem, okay, once we expanded it. Simplifying, you'll have u plus 21 times the natural log of the absolute value of u plus your arbitrary constant c that we have now. We're going to now back substitute, and with that back substitution, you'll have x minus 21, remember that was our value of u, plus 21 times the natural log of the absolute value of x minus 21, plus c. Combine the negative 21 with the arbitrary constant c to end up with x plus 21 times the natural log of the absolute value of x minus 21 plus c as your final answer. Red box it. That was problem number 6. Hope you enjoyed it. That was a good example that's going to help you out tremendously. You have no idea. All right, let's move on to problem number 7. Here in problem number 7, we have another trigonometric function involved. So that means we'll be utilizing one of those trigonometric integration formulas that I gave you at the beginning of the video. I'm going to start out by pulling out this constant using the multiple constant property of integration here. And you'll have 1/3 times the integral of sine of 5x dx. Once rewritten, I want to identify as my variable u 5x. And then taking the derivative of that, I'll have the derivative of u equals to 5 dx. Now, this doesn't look exactly like anything from the beginning of our integral problem, right? So I think it's best that we go ahead and divide both sides by 5. Dividing both sides by 5, I'll have 1/5 du being equal to dx. So I think I can do much better with that. Substituting back in, you'll have 1/3 times 1/5 times the integral of sine u du. Simplifying, you'll have 1/15 times the integral of sine u du. This is where I'm going to integrate, and I know this is going to be where I'm going to integrate when I look back at this problem, because I'm going to use my integral extension to show this is where I integrated. And when you integrate sine of u, it becomes negative cosine of u plus c. We're going to go ahead and simplify this further. You'll have negative 1/15 cosine of u plus c. It's now that we can do our back substitution, and you'll have negative 1/15 cosine of 5x plus c as your result. Or, if you wish, you could have also written this as negative 1/15 cosine of 5x plus c. It all depends on your comfort level. If you want to make sure your instructor or yourself knows what the quantity that you're taking cosine of, then you can use your parentheses. Otherwise, either form will work. Therefore, let's go ahead and red box both versions of our answer. Done and done. You guys in the comments, let me know which version do you prefer. Do you want to make sure that your instructor and yourself knows that the quantity you're taking cosine of is 5x, or is it self-explanatory by having it written as it is in the second one? Okay, so you tell me which version you prefer. All right, let's keep it moving. Here is a reminder, guys, to set up a paid online tutorial today with your boy, Mr. Whitt, at fortbendtutoring.com. Go ahead and check out our website. And if you wish and if you need, you can set up a one-on-one paid online tutorial with me where we're set up in a webinar. It's going to be me, you, and the math problems as I explain how to solve them. All right. So you get me as your personalized tutor, and I look forward to seeing you online. All right. So check that out, guys. All right. Moving back to our video, we're on to problem number 8 with the integral of x times the square root of 2x minus 1 dx. And notice that if I try to choose x, that's not going to look like what's underneath that radical there. No. If you choose 2x minus 1, you take the derivative of that. It's not going to look like x. No, that would be 2. Yeah, not x. So being as though that's the case, we're going to keep in mind what we learned from problem number 6 now, aren't we? Right? And we're going to go ahead and say that our u variable is going to be representing the value 2x minus 1. And we're going to find the derivative of both sides. You'll have du equals to 2 dx, and then you'll probably want to divide both sides by 2. All right, 2 dx is not going to help us, but we could probably get more work done with 1/2 du being equal to dx. Yeah. All right. You want to also solve for x. Why? Because look at the beginning of our integration problem. You have x as the first value that's going to hit you in the face, right? So go ahead and have that u being equal to 2x minus 1. Go ahead and solve for x by adding 1 to both sides of the equation there. You'll have now u plus 1 equals to 2x, and you'll want to divide both sides by 2, right? All right, just like that. So you'll find out that x is equal to u plus 1 divided by 2. So now that we have these things solved for, we're going to be taking those different aspects of the problem and plugging them back into the original integral problem. It's going to look like this. You'll have 1/2 the integral of the quantity u plus 1 divided by 2 times u to the 1/2 du. And what we'll do with this is we're going to go ahead and factor out that 1/2. And so you'll have 1/2 times the integral of 1/2 times the quantity of u plus 1 times u to the 1/2 du. Pulling that additional 1/2 in front of the integral symbol, you'll have 1/4 times the integral of u plus 1 times u to the 1/2 du. We can distribute that u to the 1/2 within the parentheses. And when we do that, you'll have 1/4 times the integral of u to the 3/2 plus u to the 1/2 du. So now that I have this, I want to expand this problem using the sum or difference property of integration. I'm going to rewrite it as 1/4 times the integral of u to the 3/2 du plus 1/4 times the integral of u to the 1/2 du. All right, so now I have that set up. Now I'm going to begin using the power rule and integrate. So we're going to have 1/4. There's my integral extension there. Using the power rule, you'll have u to the 5/2 divided by 5/2 plus c1 plus 1/4 integrating. You'll have u to the 3/2 divided by 3/2 plus c2. Okay, so there we have our step after integrating. What we want to do now is we want to simplify this. So this is where all of your expertise in mathematics and algebra come in handy. Remember that our arbitrary constants will be combined into one arbitrary constant. I'm now going to show that we can rewrite our complex fractions as 2/5 times 1/4 u to the 5/2 plus 2/3 times 1/4 u to the 3/2 plus our combined arbitrary constant. Simplifying, you'll have 1/10 u to the 5/2 plus 1/6 u to the 3/2 plus your arbitrary constant. We can continue to simplify this and try to combine our u's into one term. Let's go ahead and see what happens with a common denominator of 30. We'll have 3u to the 5/2 over 30 plus 5u to the 3/2 over 30 plus c. Don't forget the arbitrary constant. Then let's factor out of the two terms in our combined numerator. Let's factor out u to the 3/2. What does that do for us? That leaves us with 3u plus 5 all over 30 plus c. Now let's back substitute. You'll have the quantity of 2x minus 1 raised to the 3/2 power times 3 times 2x minus 1 plus 5 all over 30 plus c. Simplifying, you'll have the quantity of 2x minus 1 raised to the 3/2 power times 6x minus 3 plus 5 all over 30 plus c. Combining your like terms inside the second set of parentheses, you'll have the quantity of 2x minus 1 raised to the 3/2 times 6x plus 2 all over 30 plus c. Let's factor out 2 in the second set of parentheses. You'll have 2 times the quantity of 2x minus 1 raised to the 3/2 times 3x plus 1 divided by 30 plus c. Now you can simplify this, showing that 2 goes into 30. That'll be 15 now, right? So you'll have the quantity of 2x minus 1 raised to the 3/2 times 3x plus 1 all over 15 plus c. And this is your final answer simplified. Red. Box it, people. How was that one? That was a great example to show you guys, yeah? With these sets of problems, you're going to be heading in the right direction as far as mastering this content. I'm really excited about this, okay? Let's go ahead and move on to problem number 9. Problem number 9, guys, we have a definite integral in this problem. When you have definite integrals, there's no need for an arbitrary constant because you have enough information to give the result as a value. All right. In most cases, there are some cases where they throw in extra variables and whatnot, but this particular problem, you have enough information to give a value at the end. All right. An actual number. So let's go ahead and see how a change of variables can assist in a definite integration problem. How about that, guys? So these are like bonus problems on top of the other great examples that we've already given you, okay? So that being the case, I want to identify my u variable as 2x plus 1, all right? Taking the derivative of both sides, you'll have du equals to 2 dx, just like that. We'll go ahead and divide both sides by 2, all right? And you'll end up with 1/2 du being equal to dx. We'll go ahead and do a rewrite on the original problem and show that it's going to be 1/2 the integral from 0 to 4 of 1 over the square root of u du. Okay, we can also write this as 1/2 the integral from 0 to 4 of 1 over u to the 1/2, all right? And that's still du. And this could equal to 1/2 the integral from 0 to 4 of u to the negative 1/2 du. So just showing my algebra skills here, guys. Rewriting, manipulating the problem, and rewriting it using negative exponents. All right, so now that I have this, look at the format. It looks perfect for the power rule, and that's exactly why I went through all of that. So integrating now, you'll have 1/2 times, going from 0 to 4, we'll have u to the 1/2 divided by 1/2, and you don't need a c, guys. You do not need a c because we have our definite integral in play. The 1/2s here will cancel out. So this will be equal to our integral extension here going from 0 to 4 of u to the 1/2. And now we'll use our back substitution, knowing that our u is equivalent to 2x plus 1, right? And now plugging in our values, you're going to be plugging in the number at the top of our integral extension first, minus the same expression, but in the second part, you'll be plugging in the bottom number. So let me show you what that looks like with the definite integrals. You'll have the quantity of 2 times 4 plus 1 raised to the 1/2 minus 2 times 0 plus 1 raised to the 1/2. Okay, so that's going to be our setup. Simplifying, you'll have 8 plus 1 raised to the 1/2 minus 0 plus 1 raised to the 1/2. And now you'll have the square root of 9 minus the square root of 1. Knowing that that rational exponent of 1/2 is equivalent to the square root of a value, you'll now have 3 minus 1 equals to 2. And that's it. Red, box it, people. That's it. That is the answer to problem number 9. So that was another example as to how u-substitution can help you even when dealing with definite integrals, all right? And especially with definite integrals. So once you have a mastery of the change of variables technique, you can utilize that in many different areas in calculus. All right, so let's move on to our last problem, problem number 10. Here we have problem number 10, another definite integral. We have it from 0 to the power of 2 of cosine of 2x over 3 dx, right? Let's go ahead and say that our u is going to be equal to 2x over 3. How about that? Okay, or you could write it as 2/3 x. That may be a little bit more comfortable for everyone involved. Here, our derivative is going to be du equals to 2/3 dx. Well, if I were to multiply both sides by 3/2, so I'll have 3/2 du. This equals to 3/2 times 2/3 dx. What happens is you'll have the 3/2 du being equal to dx. So we'll keep that in mind. And what we'll do now is we'll substitute this back in our original integral, and you'll have 3/2 times the integral from 0 to pi over 2 of cosine u du. You'll now integrate, and you'll have 3/2. We'll use that integral extension from 0 to pi over 2, showing that this is where we're going to integrate. Integrating cosine gives you sine of u. And once again, you don't need the arbitrary constant because this is a definite integral, okay? It's now that we'll back substitute in here, and you'll have 3/2 going from 0 to pi over 2 of sine of 2x over 3. We'll keep our coefficient of 3/2 on the outside while we show that we're going to be plugging in our values. Remember, we plug in the top value minus plugging in the bottom value from our integral extension, okay? So I'll have sine of 2 times pi over 2 over 3 minus sine of 2 times 0 over 3. Simplifying, you'll have 3/2 times sine of pi over 3 minus sine of 0. Well, sine of pi over 3 is sine at 60 degrees. Well, sine of 60 degrees is going to give you square root of 3 over 2. Minus sine of 0, well, that's just 0. So we essentially are going to be multiplying 3/2 times the square root of 3 over 2. So this equals to 3 times the square root of 3 all over 4. Red, box it. Just like that, guys. And that is the answer to problem number 10. So there you had 10 examples from FBT and Mr. Whitt. As a reminder, guys, please subscribe to Fort Bend Tutoring. FBT is your boy, Mr. Whitt. I want you to like, subscribe, please comment, give me some feedback, guys. Click on that notification bell icon. Peace. Thanks for watching. We appreciate you hanging out with Fort Bend Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT. Oh yeah, baby.